book.
Thanks, Shivani. So I have not timed this talk, so if you want to interrupt at any point, ask questions, comment, by all means do so. I've been working on this for a while, but it's definitely a work in progress, and so I really value other people's perspectives on things. Okay, so as mentioned, I'm talking about Zag Smalltalk, and Zag is called Zag because it was originally going to be called AST Smalltalk, but because I was doing the implementation in Zig, it seemed to make sense to call the VM Zag. Anyway, that's just my crazy perspective. So what I was trying to do was to sort of take a clean sheet of paper and say, okay, if we're designing a Smalltalk to run on modern machines, what should some of those principles be? And so the first, and some of this actually shares some ideas with MIST, which some of you may be aware of. Some of the same principles, but quite different implementation. Because MIST is absolutely reflective. There is no C involved, and or anything else, any other low-level language, whereas Zag has a very definite Zig core. Anyway, so the first of these is large memories. So I'm not particularly concerned about using up memory. So things, if I can do something faster with taking a bit more memory, I'm prepared to do that. So that's the first. I'm not trying to implement this for 64-bit architectures, although Zig will compile my code to a vast number of different targets, and so presumably it would work fine in those contexts. But I'm assuming 64-bit and assuming IEEE 768 floating point. Also multi-core. Most Smalltalks are single core, can only use a single core for, at least for the Smalltalk. They can use the additional cores for some kinds of IO related things, but the Smalltalk is single core. And so from the beginning, this is intended to be multi-threaded over multi-cores. And I wanted to try and make it fast. So we're making some progress. So it's a from scratch implementation. The low level is implemented in Zig. If you're not familiar with Zig, it is a relatively new language, a couple of years old, that is targeted to replace C, as opposed to Rust, which is sort of targeted to replace C++. So I started this implementation in Rust and was finding it frustrating because it was doing things for me that I didn't need and not letting me do things I did need to do. So then I discovered Zig, and I've translated everything over to Zig now, and it's going well. Zig is a very interesting language. I'm not going to expand upon its attributes right now, but it's a very interesting language. My goal is to support anything that runs currently on Open Smalltalk. In other words, I'm trying to make it as compatible as possible with the Open Smalltalk VM, although there are a few differences that would require some code to be rewritten. And the reason is I don't want to rewrite userland. Userland is fine. It's the VMs that I think could use some work, or new eyes at least. So some key features, it has 64-bit immediates. So all double precision floating point numbers, small integers, true, false, nil, all symbols, all Unicode characters are all atomic values, immediate values. And the next is that it uses copying collectors per thread, per core. And the stack is per core, and then it has a non-moving arena for longer living things. One of the research questions is to speed up dispatch, because I'll talk about it more when I get there. I wanted to be able to generate code relatively easily from an AST, and currently it's using a threaded code execution, which I'll talk more about later, and in the future I'm hoping to have a JIT that's attached to it. So immediate values are all 64-bit, and they use NAND boxing. I'll just describe NAND boxing very quickly for those that are perhaps don't know about it. But basically, any 64-bit quantity that has all of the exponent bits 1 is not a valid, not a number in double precision floating point. And that means that you can use those other 52 bits for lots of interesting things. And so as I said, I have coded all of these things within the 64-bit not number of values, as well as pointers to objects or heap objects. And there's room for any type that has a single 32-bit value to have an immediate implementation of it as well. So I won't go through this in any great detail, but so these are all everything below FFFFF0, so up to negative infinity. These are all considered double precision floating point values. So there's no encoding on those. So basically anything that in an unsigned compare is less than or equal to minus infinity is a double precision floating point. Similarly, anything that is greater than or equal to FFF8 000 is a small integer. So the small integers are at the top of the address space, the doubles are at the bottom of it, and then everything else is coded in between. There's some values here that could be used if you, for future expansion, where you needed to have other things that had 48-bit values, because you have 48 bits remaining here. But at the moment, I don't see a need for that. FFF7 are all the heap pointers. So 48 bits available for the heap pointer, which supports all current architectures, or at least all commercial architectures, but everything is 8-byte aligned, so you could get 3 more bits out of this if you really needed to. Then all the other immediate values are coded as FFF6, and then this is the class number. So this uses 16 bits for class numbers, and so all the so these first 3 are reserved, and then we have false, true, undefined. Symbols are coded here as a 24-bit symbol value index and a 8-byte or 8-bit arity tag. So from the symbol, you can tell what its arity is. You don't have to go and look at the string or anything. And all Unicode characters are coded here within this this code. And this is what I meant by anything else that had, you could code the class and 32-bit values down here for any other value that had a unique 32-bit value. So multi-core support. So the only way to speed up applications in this modern world is to use more cores. They're not making faster cores, they're making more cores. And so having Smalltalk constrained to using a single core, despite how creative people have been about how to use other cores for other things, if you can only have one core that's actually doing computation, that is certainly a problem. We want to have minimal blocking between those cores. And so we have computational mutator threads. Typically, you in your application, you would probably create enough threads to use up all the cores that you have on your machine. And then we have IO threads as well, typically one per open IO port or file. Sorry? No? Okay. And then there is a global collector thread that runs periodically to collect the global arena. So the mutator threads use a copying collector. They have a private nursery, which includes the stack. So the, fairly traditionally, heap grows up, stack grows down within their private nursery. There are 2 teen arenas also per mutator or per core. And so when the nursery gets full, then we copy into the current teen area, and then we copy back and forth between the teen areas until things have been, if they've been copied back and forth enough times, then we say, okay, well, fine, we'll promote that to permanent storage. But otherwise, if it's not being used by any other core, we'll keep it in our teen arenas, and we'll copy them back and forth because that's very efficient and doesn't interfere with any other threads.
Very familiar. I'm sure you've seen demographic feedback mediated promotion.
Yes.
This is exactly this. Go ahead. Sorry.
I'm not saying claiming that this part is novel.
Yeah.
Particularly, I'm just
No, I'm not fetching. I'm just smiling that you landed on the same thing I did for the original generation scavenging scheme.
And I believe GNU Smalltalk does a similar model. They inverted it. They have a large, like a huge nursery and two small teen areas. Anyway, I don't understand why they made that choice, but this seems to me like the more natural approach. And then what happens is when the global collector wants to do a mark of the global area, it sets a flag in the thread, and the thread, next time it gets a chance, notices and says, oh, okay, then I'll go and find all my references to global stack, or to the global arena, sorry, that should say arena, and I'll mark them. So all the threads, all the mutator threads can mark in parallel with very little interference. They can use spin locks to lock the pages that have those marks in them. And then once they've marked their stack, then they just proceed, and they can continue to work at full speed, and even can allocate things in or promote things into the global arena or allocate in the global arena.
Oh no.
IO threads just maintain a list of current shared buffers.
Yeah.
So that the comment? Okay. A list of shared buffers while the IO is blocked, because an IO could block indefinitely, and so we don't want to hold up our marked sweep of the global area while that's happening. The global collector uses a non-moving mark and sweep arena, and so it periodically does a mark. So it marks any known shared structures, so the class table, symbol table, dispatch tables. Then it asks the mutators for their global roots, and then it processes all these till all the roots have been found. So small detail I just mentioned. So when you mark, no, I guess I'll talk about it in a minute, sorry. And then once everything's marked, then it can do the sweep on these. Okay, so the global collector does this non-moving mark and sweep, and it uses a linked free list heap. So it allocates chunks, multiple page size chunks, and allocates within those. It uses, similar to MIST, it uses power of two sizes, and it has a linked list for every one of the power of two sizes up to the size of a whatever this allocation amount is. What this means is that to allocate something, it's very quick. You just find the linked list that it is part of, and take the first thing off the linked list and use it. And then when collection is done, free space is returned to the largest linked list that you can find. At any point, if you look at the linked list for a particular size object and there's nothing there, then what you do is get a larger one and split it, and then put the new free one on the free list, and then use the other half of that larger object. Large objects, ones that are larger than one of these allocation units, are separately mapped. So there's a special header for an object that says that this object actually has its storage somewhere else. And so the object will just have the instance variables, and then the array portion of that object would be a pointer and a size to a page or a sequence of pages. It could be as big as you want, that will contain the actual data for that large object. The reason for this is that if you don't do that and you allocate large objects, they will typically extend over multiple areas, and then when you collect them, they will get broken up over time. You know, when the object goes away, subsequently, as we do allocations, that object will get broken up, and you'll never actually get that memory back, because it'll have some pieces of every one of those pages will be active. So by making large objects be in separate address spaces, it means that you don't have this problem. Basically, when the link, or when the object that references this global area or this extra area becomes free, then we go and we free up that, give it back to the operating system. So this means that you could do a memory map of, you know, some massive file, and it doesn't cause any real garbage collector impact. Heap objects have this is the structure. So they have a length, 12 bits, which is the number of long words, 8-byte words beyond the header. So that means that beyond this word, actually. So it tells you basically how many instance variables there are, if there are instance variables. So object could have just instance variables, in which case this will be the number of instance variables. They could have just indexable variables, in which case this would be the size of it up to the maximum possible. Or they could have both, in which case this will be the number of instance variables, and then there will be a separate size for the indexable area. And the size of the indexable area, whether it's in the header or whether it's in this length field, or it's later in the object, would be what would say this is actually an external object and is linked separately. There's a 4-bit age. So this is actually wrong, sorry. So 0 means it's on the stack and has not been moved to a heap yet. And the only thing that can be is a context, which we'll talk a bit about later. 1 means it's in the nursery part of the heap. And then 2 to 7 mean it's somewhere in the teen. And when it gets to 7, and we would bump to 8, is when we move it into the global area. And then 8 and above are used, means it's in the global arena, and the other 3 bits are used as the mark bits for the object. Then there's a format, which is somewhat similar to the encoding that Spur uses. So it encodes this if it has array fields, then it encodes the size of those. It also encodes whether there are index variables that have pointers, or any pointers in the index variables, and separately whether there are any pointers in the indexable area. And what this means is that the garbage collector can very quickly skip over things that don't have any pointers in either of those areas. So this makes garbage collection significantly faster. Strings are stored as UTF-8. So this is an incompatibility with standard Smalltalks, because that essentially means they're not mutable, because you could break the UTF-8 encoding if you mutated them. So that is a possibly small, hopefully small, but an incompatibility between this and other Smalltalk. So one of the ways that I think that this can be, or that Smalltalk can be speeded up, is what I'm calling unified dispatch. And what this means is that there is, for most operations, a single level of hashing for method dispatch. So the way this works is that each class dispatch table has an entry for every method that has been sent. So if you send a message to an object instance of a class, then what happens is it's either already there, in which case it dispatches to it and everything is good. If it's not, then the NU code essentially goes and looks to see whether there is a source for that, in which case it will compile it and add it to the class dispatch table. And if the dispatch table gets too big, then it replaces the dispatch table with a larger one, a rehashed one, so in other words, whatever method got sent a message, or whatever class got sent a message, will have an actual implementation of every method that's been sent. And the reason for this is that this gives tremendous, well, two things. One is that it's faster because you don't have to hash at multiple levels. So if you don't find it at one level, you don't have to go up to a higher level generally, although it can do that if necessary. Because there might be some things that are so common and so rarely used that you don't really want to compile them into every class. But in principle, they're all there. But the other significant advantage is that when you're compiling this method, you now know everything about it. You know who its superclasses are. You know what self stands for in that method. You know exactly. You don't have to worry about it being a subclass or a subinstance, because there aren't any. This is the object that actually got sent the message. So you know the type of self, and this gives a lot of optimization opportunities, or at least so I believe. So I'm claiming, which will allow you to do a lot of optimizations that are not generally available. One of the challenges with optimization is obviously that you need as large a body of code as possible, so that you can see optimizations, things that are used here and not there. So we do, I'll talk about it in a couple minutes, very aggressive inlining to inline as much code as possible into that method. So messages to self, messages to known types, messages to super, all will be inlined into this method that we're in the middle of compiling. Yes, Dave.
The key questions about inlining are: what do you do about loops? Do you crawl up the stack to inline the whole loop body? And what do you do about changing a method that's been inlined so the effect is what you would expect? You know, inline, but you're not executing that inline method right now.
Right. So if there's any change to a method, then you just invalidate them all, because you'll recompile it when necessary. And loops will be inlined because you're sending a message, and so that message will be inlined, and so the whole body of the loop will end up in the method. And so blocks, any message that you pass a block to, for example, that block will be, or that method will be inlined, so the block will be inlined as well.
But might the method be called from another method that's called from another method that's in the middle of a loop?
So if it's not a, yeah, I don't think there's a problem, but
Let's talk about it later. I don't mean to
Sure.
stall you, but
Yeah,
these
yeah.
two problems are pretty interesting and need to see what you're doing. Go ahead, Dave. Thanks for taking the
Okay.
question.
Thanks. Yeah, so the next aspect of this hashing is that I'm using phi hashing, which is a very interesting way of doing hashing that has very, very good characteristics. And I'm generating essentially a near perfect hash. So I allocate a hash large enough to capture the keys, but there's always the potential of having a collision. And so what it does is it actually encodes a collision into a pointer to a secondary table. So it will minimize support up to a certain number of these per hash table, and it will grow the hash table big enough that it can get it within that number. But from the experimentation I've done with existing classes, I get very, very, very few conflicts in the hashing. So it's near perfect hashing. And the other reason for using unified dispatch is that there are lots of optimizations that other Smalltalks use, but those Smalltalks don't work well in multi-core environments. Because if you're going to modify a method, for example, to use the Deutsch dispatch, that would mean you'd have to lock the method. What if it's in the middle of being executed? I mean, it gets really complicated to get that right. And so I don't want to do that. So I would need to get the optimization happening at the dispatch level, not at using other mechanisms, or at least so I believe. So inlining, no special case for ifTrue, whileTrue, or any of those. References to self-super, code, or inline, references to any known classes, especially where there's a small, not any known classes, but any known classes, but also messages that have a small number of implementations, like ifTrue, ifFalse on most systems has 2 implementations. And so we would inline that just because there are only 2 implementations. So we could just switch based on which class that is and inline the code. So we'd inline both of those methods and go to the appropriate one. This means that most blocks are going to be inlined. So we're not going to have, non-local return is not particularly expensive. I think non-local return is not going to be particularly expensive because of some other things I do as well, but it shouldn't be that common that there's a true non-local return because everything should be inlined. So most blocks don't get created, and it provides large compilation units for optimization purposes. Code generation. So there is no interpreter. Everything is generated into a threaded execution model. So I'm not sure how many people are familiar with threaded execution, but the idea is that a threaded method is a sequence of addresses of code. And this certainly is widely used in languages like Forth. I think it actually predates Forth. Busy tracking down the exact history of this, but it certainly was used in, as you can tell, I'm old. The second computer I programmed on was a PDP-11, and the Fortran compiler that came with PDP-11 used threaded code as its code generation model because it was easy for them to get a decent compiler very quickly. And so I have the paper, a reference to the paper that talks about that, and that's the earliest that I've got on this. In any case, it's a sequence of addresses, and the idea is that you call the next method. So essentially, you have a secondary program counter, and you execute your code, and then when you're done that code, you jump indirect to the address pointed to by that value and advance the secondary program counter. And what this means is essentially you execute some code and then you jump to some other code and then you jump to some other code. So these are not calls, they're so a sequence of Zig function addresses. And Zig one of the reasons I like Zig is it has a tail call, or like a mandatory compile time, or if it can't do it, it'll give you an error kind of tail call elimination. And I pass the program counter for this this threaded program counter. I pass a stack pointer, a heap pointer, reference to the thread, and a reference to the current context. And this is used for primitives and control implementations. And I'll show you the code a bit later, or some example code a bit later.
Let me just mention that the first jitter that was created for Squeak by Yampio Marta was a threaded system. So, and it was
yes,
inspired by.
I have a reference to that paper. Yeah. Sorry, it was
okay.
inspired by?
Edith Miranda had done a Smalltalk called Brouhaha or something like that. I
have
the name
too.
That used threaded code as well.
Yeah.
Well, and you know that Peter Deutsch created the first JIT for Smalltalk, as far as I know, in the PS system, written in assembly for the Sun workstation, that did peephole translation and optimization from bytecodes to, I think it was 68,000 machine code. That was way before the Squeak stuff, but go ahead, sorry.
That was 1984 there for the Peter Deutsch paper, Popple.
Precisely.
Yes.
Thanks, Tim.
Yeah, I have the Peter Deutsch paper too.
I should also point out that Ian's threaded JIT for Squeak, because of a mistake in how some caching related invalidation thing actually ran slower, at least on ARM machines, which was terribly, terribly upsetting after doing all the work.
Yes, I can imagine. Yeah, I'll show you some very preliminary benchmark data later, but yes. So this works really, I mean, because of Zig support, this becomes very, very clean and easy to do. So I'm really happy with that, the way it works, and some other features that I'll mention in a minute. So the intention is to have a JIT in the future, but so all the optimizations will happen, or 99% of the optimizations will happen generating the threaded execution code. And then the translation, the JITting, will be actually fairly straightforward. There will be relatively few optimizations that are done there. And interestingly, the way to make this work is to use continuation passing style. And I don't know how many people here are familiar with the scheme world and what continuation passing style means, but I'll show you an example in a few minutes. And the idea is that the method that you have gets broken up into multiple methods, each of which is has no loops or calls in it. All the calls will be a boundary, or the loops will be a boundary of the. Actually, there can be loops, but not loops that have a call in them. Any loop or any call will be a boundary that has to be built into a separate method. And as I said, I'll show you an example in a minute. One of the really cool things, and so I'm going to use the LVM jitter for this, but one of the really cool things about this is that it gives me an almost seamless transition between native and threaded execution. So what happens is that I have my threaded code, which has a sequence of addresses. And by making the JIT'ed code have the same type signature, same parameters as the threaded units, whatever they might be, I can call them interchangeably. So what I can do is I make the first method call, if you like, or instruction, threaded instruction, be a no-op. And then I have whatever code I have, and I'll show you in a few minutes. And then I can, at any point, I can replace that word with the address of a JIT'ed code. And the next time that gets called, it just executes as if it was doing the normal thing. It does the threaded call, but the threaded call, instead of doing the no-op, happens to go off and execute the JIT code. And so I get the seamless transition. The JIT code also, or the JIT'ed code also maintains the virtual program counter that it would have. So typically the JIT'ed code will have the equivalent of several threaded instructions in each of the code blocks, each of the CPS code blocks. And when it passes control to the next one, it remembers what the program counter for the equivalent code would have been. And what this means is that if you get an error or you want to debug at any point in time, basically you just change the return address, and I'll show you a bit about this in a minute, but you change the return address to be run the threaded code rather than run the JIT'ed code. And now when you return from that function, it automatically goes back into threaded code mode. In the threaded code mode, you can do single stepping. And so you can actually single step. So you can go from running at full JIT speed to running at single stepping without any recompilation, without any invalidation. So certainly in the OpenVM Smalltalk, if you have to go into debugging mode, it basically ignores all the JIT'ed code and goes back into a byte interpretation mode. Here it goes back into the threaded interpretation mode rather than the JIT'ed mode, but it doesn't have to do any extra work on this. The JIT'ed code is still there and could be re-enabled at any point in time. So there's this very seamless transition. So there's no complicated trampolines and whatever the opposite of trampolines are. So all that, so Elliot called it however you pronounce trampoline backwards, but anyway, so none of that has to happen. It's all very seamless transition between them, which I'm really happy about, and I didn't really expect when I first started thinking about the threaded execution. And then I'm also going to have a standalone generator because I've done a lot of work with Pharo.js, where we're generating standalone JavaScript code. The idea of generating standalone code for applications makes sense to me. And so this is a tiny variance on the JIT'ed code. Just instead of generating JIT code, I generate Zig source code. So contexts are interesting. This is another area where I'm not sure yet whether I will be able to replicate the API exactly for standard contexts. But so context is used for any method call, as it is in every Smalltalk, but they're created lazily on the stack. So there's a stack of them, and they're created lazily. So we only create them, first of all, we only create them if you send a message. So what this means is, just as most Smalltalks, if you have a primitive call, it doesn't create the context until it's decided it can't, that the primitive is not going to do the job. So we certainly do that. But also we can postpone creating the context later. So if we have something that doesn't have a primitive, but it doesn't make any calls, then we don't need a context. So we can continue to execute through without having created the context until we actually need it. So we create them lazily. And we create them somewhat incompletely initially, because until it goes on the heap, it doesn't actually have to have all of its properties just right. So the header, when the context is created, a default header gets created. It's not the right header. It's just it basically says I'm allocated on the stack. So it's a constant that basically gets stored there. It's not calculated in any way. Then there is a threaded program counter, which points to the next threaded node that it's supposed to execute. And then there's a native program counter. And the native program counter is used for continuation passing style. And if you're executing in threaded mode, then when the context is created, this gets filled in with, I guess you could call it a trampoline. It's basically a one instruction method that will continue back into the threaded mode. But if it's a native code, then what would be stored in here would be the CPS for the next, the address of the next function in the execution. And the threaded program counter in that case is stored just to allow us to fall back into single stepping mode at some point in time if we want. So when we leave one piece of the CPS code and we move to the next, the threaded program counter will be updated to the appropriate place in the code so that we can return. Then when there's a size field, so this is an object, and the first two fields, the TPC and the NPC, are considered to be instance variables, and then the rest is considered to be an array. And the instance variables are tagged as not having pointers because they are not they're not normal Smalltalk objects. But then all the instance variables or all the index variables are coded to have potential pointers in them. So we have a link to the previous context, a link to the method, and the temporaries, and then the parameters. So the temporaries are initialized to nil, of course. The method is set up, and the previous context is set up on creation. And as I said, a default value is written into the header because it's cheap to do. And if it's a threaded execution, the NPC will be filled in as well. The TPC will only be filled in at the call, and the size and the header will only be filled in if this context gets migrated to a heap. So if it stays on the stack and we never has to be reified to the heap, then we don't bother even filling in those fields. Not that it saves a huge amount, but it saves a few instructions on every method call, essentially. So results. So the only benchmark I have at the moment is this ridiculous 40 Fibonacci, and I do have some results. So running on Pharaoh, this is Pharaoh 11, and this is run on an M1 and also an Intel architecture. So you can see that, so Fib native is just written in Zig. It just does Fibonacci in Zig, and so it's the sort of the gold standard. We can't do better than that. Pharaoh is execution in Pharaoh, and FibComp is the hand compiled code that would be produced by the JIT compiler. Okay, so it's hand wavy, but been fairly careful to not overstate that. So, and then the threaded code is the thread, the sequence of thread instructions. And the fib byte I just finished moments before this lecture started. A byte interpreter. So this is a bytecode interpreter, uses the same optimized thread instructions and so on that are same optimized instructions that the threaded version would use. And as you can see, it's about 7 times slower. So the bytecoded version, this threaded interpreter, Josel and Tim, you were commenting on Ian's implementation as having been slow. This threaded execution is about 7 times faster than the bytecoded version. And then the JIT'ed version is about 5 times faster than that. And it's a little bit faster than the Pharaoh version. I am very happy with this result because this is significantly, because it's Fibonacci, it's significantly about method calls and method returns. And I believe that once my optimization is working, that I will have relatively few of those. And so I will get, I think I will run many times faster than And in fact, I think the threaded version will probably come close to the execution speed of Vero, but we won't know that until I actually have results. So thought I'd show you a little bit of the code, and I tried to paste it into the slides, but I couldn't. So I'm going to stop sharing and then share something else. So, what is it? Not that. So, can you see this okay, or should I increase the font size? Okay.
I find it just about okay.
Okay, well, I'll bump that.
Okay. Yeah, go with that. I think that's fair compromise.
Okay. So this is Zig code, and so here's just the comment. This is the native version. Not surprisingly, it takes a U64 and returns a U64 unsigned 64-bit number and does the obvious. Okay, I'm going to skip over this comp code for a minute and go down to the threaded code. So this is what the threaded code looks like. And so I have one of the nice things about Zig is you can write, it doesn't have a macro system, but types are first class, and it has a compile time execution. So you can do the equivalent of macros, except arguably better. Anyway, so I've written this as something that can parse these strings and so on. So this is a label if it's a string with it ends in a colon, and it's a reference to a label if it's a string that doesn't have a colon. So so we come into this code with on top of the stack is the number. So we know that we're compiling this in small integer or an integer. So or small integer, because 40, the number I sent it to, is a small integer. So I know that it's going to be a small integer. So there's a small integer sitting on top of the stack. So the first thing I want to do is compare it with 2. So I duplicate that value, and then the simplistic code would call, sorry, that should be push literal. Simplistic code would call a generic push literal and encode the actual literal value. But because things like 1 and 2 and so are so common, there's a push literal 2, which just does that. So it just makes it a bit shorter. Then the next thing we need to do, somebody's mic is on. It's okay, but so then I need to compare. So I use primitive 5, and if primitive 5 succeeds, then it's going to label 1. Otherwise, I have a primitive failure. And so this is the sort of unoptimized code that I would use. But because I know that self is an integer, small integer, and I know that 2 is a small integer, I can do that comparison without having to check to make sure that they're small integers. And so this is an alternate version of this that can't fail, and therefore I don't need the label and the primitive failure. So now this will have replaced those 2 values with a Boolean. So I then check to see if it's false, and if it is, I branch to label 3 down here. Otherwise, I drop self off the stack because I don't need it anymore because I'm going to return 1. So I drop self off the stack, push a literal 1, and then return. Notice that I haven't created a context here. So there is no context. So this is a very short path to do this execution. But if I get to label 3, then it wasn't less than 2, and therefore, or less than or equal to 2. So therefore, I'm going to have to create a context. So that's what label 3 does. So I create a context. This says the current method. Then I need to, what do I need to do? I need to subtract 1 from that value. So, no, sorry, I push the temp 1. That's a reference to self. So I push self on the stack. So it's temporary number 1 in the index list. Then Again, I could do a push literal and do a comparison, but again, that's a very common operation, comparing with 1 and 0 and a couple others. So I replaced those two with a push compare, or sorry, this is subtract literal 1. Because of the way integers are coded, this actually, you can subtract an untagged integer from a tagged integer, and all you have to check is that the result is a proper integer for small integers. So I do that. It could cause a failure because the result, I could have had overflow or underflow. And so if it fails, I'll branch to label 4. No, if it doesn't branch, if it's successful, it'll branch to label 4. And then here's where I do the recursive call. So I'm going to do a call local. Can I do this rather than have to send? Well, because I'm compiling this code and it's a send to self. So I know that, or it's a send to this self -1. So I know that it's a small integer. So I know that this is where the code goes, and therefore I don't have to do the expense of doing a send. I can just recurse. So this does a local call back to this code, and now we'll check that n-1 value. Then when that returns, I push self again, and then I do a subtract constant 2, again, knowing that they're both small integers, so we're good. And then I call recursively to calculate the second Fibonacci number. When it returns from there, the stack has the sum of, or those two Fibonacci numbers. I add those together, possibly with success going to label 6, possibly failure. Label 6, I do a return the top thing on the stack. So I have a closure on the stack. So the top thing, where the stack is right now, isn't the return spot that I need. So I need to do a full return that's going to skip over that that context and fill in the value and return. Okay, that was very fast, I realize, but gives you some idea, hopefully, of what it looks like. So here is what would be JIT'ed code. And so here I have, so this is the compiled Fibonacci. And we do very similar things. We check to see, we compare the thing on top of the stack with the constant 2. If it's, this is less than or equal to, if it's less than or equal to, then I'm going to replace the thing on the stack with the number 1. And I'll do a tail call return to the caller's native program counter, which will be, in the case that I was called from a native code, it will be the actual address of the continuation. If I was called from a threaded code, then it will be the trampoline, if you like, the one instruction trampoline, which would convert me back into threaded mode. And I pass in the threaded PC that I got from the context. I pass in the stack pointer because I didn't change it, the heap pointer, the thread in the context. So this is a tail call. So all it turns into is a branch. So this becomes a branch. So the system stack is not used at all, by effectively not used at all. The stack pointer stays in the same place. Within one of these compiled codes, which might be a primitive, I could call something and use the system stack, and that would be fine. But by the time I pass control to the next stage, I'm back to the original stack. So that was if it was less than or equal to 2. Otherwise, I create a context. And this is just the magic incantations to create the context. I'm going to push something onto the stack. So this is a new stack pointer, which is going to be 1 advanced. Parameters are immutable in Zig, so that's why it's new HP and new SP. Then I'm going to calculate the self -1. So I I know that these are both integers, so I can call the I here is inlined. So this is inline code, which is going to compare, or it's going to subtract 1 from the top of the stack. It gives me a new stack self -1, store that into the new stack that was created as part of this context. And now I set the threaded program counter to the appropriate offset. So this is the program counter I was given was the one at the beginning of the method here. And now I'm about to do the equivalent of this call local. And so this is the program or the threaded program counter that I want on return. So that's what that's what the +15 is. And this is compile time knowable. I say that the native program counter should be fibcomp1, and that's this code here. So this is the continuation. When the thing that I call returns, I want it to go here. So then I do another tail call, and I call back to myself to do the Fibonacci of n-1. When it returns, it'll come back here. And now I have a stack. I make more space on the stack, subtract 2 from it, get that new value, store it into that new stack pointer, create a new context again, update the context. Note I'm not creating a context here. I'm just updating the threaded program counter and the native program counter. So I guess I actually should have had 3 times. So on the creation of the context, a few fields get created. When you make the call, 2 fields get updated. And so in most methods that actually make several calls, it's only those 2 instructions that will actually happen for each call. Then I make another threaded call, and I say to return, or to comp, and I'm going to return to fibcomp2. So I can return to this continuation code. I don't care about the PC anymore because I'm about to return. I add the 2 things on top of the stack, and then I store that sum in the return value, in the self position in the context, and then I pop the context and return to the caller's native program counter, and off I go with whatever it was doing. So let me just show you very quickly. Not sure where this code is. So here's what so push true on the stack. So everything you see has the same parameter signature. So I'm to push true on the stack, then I make space on the stack pointer, store the value, and do a tail call to the next primitive in a row. And the same thing for primitives in the more classical primitive sense. Just checking. Okay, I don't think the questions are for me. Okay, so just go back to the talk. So, so conclusions. I think this is moving towards a fairly high performance Smalltalk. Sadly, it's not reflective. I aspire, like everybody else does, to reflective VM, but I think the ends justify the means in this case. And some of the ideas may make their way to other Smalltalks. This is, at this point, it's purely research, and I don't know whether people will sort of accept the idea that's not reflective, but and it's, although it's oriented towards Smalltalk, my plan is to support other languages. Certainly object-oriented languages like Python and Ruby would be very easy to support. and but also other languages. So I have Scheme in my sites as one of the languages I'd like to support. So, and it's available on GitHub. If anybody wants to play with it, anybody wants to contribute to it, that would be fabulous. It's not quite at a point I think that people could easily contribute to it, but it is there. So where its current status is, I've gotten the execution model, the threaded, and so the bytecode model I'm just going to abandon. That was an experiment, and I got the results I kind of expected, that it's 7 times slower than the threaded model. It's smaller, certainly. So the bytecoded version is almost the same number of codes as the threaded version, but the difference is the codes are a byte long instead of being 8 bytes long. So it's about 8 times smaller. And the threaded code is about half the size of the JIT code. So one other detail I didn't mention is I mentioned that I can replace that first threaded instruction with a pointer to the threaded code, but I can also replace it with something that says, wait one more time and then start compiling this or optimizing this. So I can generate a very dumb version of the method initially, and then I can have it say replace or try this, and so that will get called. It'll replace that word with do it next time round, and then the next time it gets called, it says, oh, okay, schedule this to be optimized, and then continues to execute, and everything happens normally until it's optimized, at which point it replaces that with the JIT'ed code, and we get the full performance. So it's this idea of having the threaded code and being able to have that first word that I can put different things in, it turns out to be extremely powerful. So that's all I had to say. So any questions? Or did I talk so fast that everybody's?
Well, I always have questions, but what prompted you to start this project?
I thought of this idea of the single level dispatch, and I was frustrated with the fact that the available Smalltalks didn't have a good multi-core story. And I realized that RoarVM and some others do, but the ideas from those don't seem to have made it into certainly not into open Smalltalk. And as far as I can tell from conversations with vendors, haven't really made it into vendor Smalltalks either. So
so a combination of wanting good performance for multi-core and being seized by this idea that you just had to try out. Is that fair?
Yeah.
Okay, cool. Thanks, Dave.
Thanks.
Dave, I have been working with do you know NIM, this language that is like, so there are like these languages now that are like, you have NIM and SIG, and there is also Go, like these languages that are like low level and system related, or trying to work with systems. And I have been working with Faro for, like, let's say, quick prototyping, and with NIM for low level stuff, like I don't know, optimizing reading, or bringing some library that is not written in Faro, and I would like to use, I don't know, improve YAML support or something like that. And when I saw Zach Smalltalk, I was thinking, just for curiosity, how difficult will be to use, for example, NIM as the, let's say, backend of a Smalltalk machine. Like you have like just, I don't know, if I want to re-implement the Blue Book, usually the path is use something like C. But I wonder if I could do something like re-implement, just for curiosity, the Blue Book with something like NIM. because
Sure.
the SAC Smalltalk is some kind of path for this kind of implementation in a way. What do you think of going the other way around? Not from SAC to several languages, but from Smalltalk to several backends like NIM or SIG or Go. Like what will be this other path that is not only using C for the, let's say, core implementation of the books, but these other languages that are more modern are approachable in a way.
So, I mean, Zag is sort of that, using Zig as the back end, but you could, I don't remember, yeah, so there's NIM and there's I don't know, Odin and
Go and
Zag
yeah.
and Rust.
Mhm.
Well, Go has a garbage collector, so that's off the
yeah.
table. And I don't remember whether NIM does or not, but, and there's D as well, but D has a garbage collector. So I mean, so I was originally started doing this in Rust, and then it was just a little bit too high level, I think, for what so I may actually, maybe get a grad student or an undergrad even to re-implement Zig re-implement Zag in Rust. That might be interesting just to compare it with Zig, and but Zig was there and gave me what I was looking for. But to write a primitive in any language that can do tail call would be pretty straightforward, I think, because the Zig uses LLVM as its back end. So if you have a language that uses LLVM as its back end and you can do tail calls, then you could write your own primitives in that other language very easily. Yeah, I mean, I like Zig, but it's an arbitrary choice. But no garbage collector is certainly part of it. And as I worked through the threaded stuff and realized how powerful that was and how much it gave me, the idea of being able to force tail calls is really is key to the structure that Zag has, at least. Not saying that you can't do it, otherwise you can, but this gave me the power to build something relatively quickly using threaded execution that I don't really need to worry about the JIT part, and that's a huge win in my mind.
Okay,
and because the execution will be still significantly faster. I mean, what I should do is I should go up and run my Fibonacci example on the open Smalltalk stack implementation, just to get a sort of production quality comparison of the byte compiler. But the byte compiler I wrote is, it's pretty good, I think. I don't think you could make it much faster. There may be some things that Zig versus C doesn't do quite as efficiently. I don't know, but short of that, the byte compiler or the byte interpreter that I wrote is pretty much as good as you're going to get. So I think that factor of 7 is real, and I trade a factor of 7 speed for a factor of 8 space pretty much anytime.
Mm-hmm. Okay.
Hi, Dave. This is
Hi.
Peter from Vancouver, and really pleased and excited that you're developing a multi-threaded Smalltalk. I've used Smalltalk since the 80s, and IBM Smalltalk, we built a big e-commerce system, but of course the limitation was that on a multi-homed, a system where I have served multiple clients on one big image, the single processor is a big limitation with Smalltalk. So my interest is mainly building web apps where I can leverage the multi-processors and multi-threading, so I'm not limited with e-commerce systems. You mentioned early in your talk that you're using as much memory as you need, or you're not, you're favoring memory if you can get execution speed. Since virtual private servers are priced based on amount of RAM and the number of CPUs. So one of my big costs is, having more RAM and having more CPUs. Does your Smalltalk use a lot more memory than other implementations of, for building web apps, whether it's PHP or whether it's C# and .NET?
I would expect it. Yeah. I don't have enough capacity to build code at the moment to be able to answer that clearly, but I expect it will be so the I don't know if I can quickly check something. Sorry, just give me a second. My expectation would be that the so the garbage collector is quite efficient, and in terms of its memory usage, so it allocates things a little bit freely, but it, for example, if you have a very large object, you're not worried about that you use for a short period of time and then it goes away. You don't have to worry about it continuing to pollute your heap so that it can't be collected. It can't be given back to the operating system. So so that is one aspect of it that I think would be support it being relatively small. I'm just checking something. So my runtime system as it currently stands, which doesn't include all the garbage collector, uses 160K of that's its text size and 16K of data. So that, and there are pieces that need to be added to it, but I don't think they're going to add to it very substantially. So I think you're talking about, probably less than 1/4 megabyte for the executable, and then the Smalltalk is going to be the methods will be a bit larger because they're threaded rather than byte coded, but the garbage collector will compensate to that to some degree. So I expect you could run some reasonable small application in, a couple megabytes. That would be what I would hope.
Oh, that's very favorable. Now, you're executing a standard, let's say, feral image, and which isn't really optimized for your type of multi-threading. What has to be done for the multi-threading implementations?
Well, feral people have been working on making things multi-thread safe, even though there aren't multiple threads in it. They've been trying to recognize, as they do sort of code reviews and so on, they have been working on it. So I don't know if there are places where so there historically, I mean, even the implementation of semaphores, for example, is some code that doesn't call any other methods and therefore is guaranteed to not be interrupted in its execution. And if there are any of those that remain, they're going to be a problem because another processor could be running exactly that same code at the same time. And so that is going to be, once a major Smalltalk adopts multi-cores, they're going to have to solve that problem. They're going to have to, work through those problems over time. And, it's kind of, you're not going to know they're there to some degree until you get there.
Thank you.
Yeah. Any other questions or comments?
I'd just say enjoy what you're doing and good luck with coming up with stuff that interests you. It's always fun doing things like this. It's always hard work.
Yes. Yes. Yeah, I suspect I went through a lot of stuff rather fast for people, but I wasn't sure quite how long it would go, and it's been an hour and a half now, so I
In the old days, we
pieces
used,
of it at some computer. Sorry, go ahead, Dave.
I'm sorry, Dave. In the old days, we used the compiler benchmark as the canonical, single core benchmark. And
Yeah.
I'll be really interested to hear how your thinking evolves as you use more benchmarks and find out more about the performance envelope of this thing you're building. Any thoughts on what you expect or what benchmarks you're going to use or what the future holds, Dave?
So I'm going to use some of the, so the compiler is not a near target, I think, realistically, but I'm some of the micro benchmarks, I don't remember them off the top of my head, but there's a couple that are fair chunks of code. So certainly trying to remember the something blue, or I don't remember, but anyway, there's
Delta Blue.
Delta Blue, yeah. So that's certainly one
Jim
of the ones
Maloney's,
that I'm.
Yeah, sorry, the delay makes it tough. Jim Maloney's diff algorithm benchmark. John Maloney. Sorry about that, John.
Yeah. So
okay, cool.
That's certainly, I want to get that one, and there's another one, Richard or something. I haven't looked at these in a while, but those are kind of the two benchmarks that I've. So in the Pharo.js work that Nori and I did, those were a couple of benchmarks that we compared how, because we compiled JavaScript to, Smalltalk to JavaScript, and we ran it on Node, for example, and also in browsers. And we had a benchmark in our paper where we compared those with Pharo, and Node was significantly faster than Pharo. And we'll see. So those are the ones that I sort of have in my mind as being a reasonable enough size that A is reachable for me in a not too distant future, and B would actually give real results rather than. I also want to do another one, which is basically just Siver Eratosthenes, just to see how my loop inlining and so on and so forth, because this Fibonacci is all about calls, right? And so I'm pleasantly surprised that my calls actually remain in competitive with Pharo. If I had something where I actually have enough code that I can inline most of it, then I would expect to kind of blow the doors off things, but we'll see.
I wanted to say that I'm very interested in including optimized C or optimized Zig numbers for all your benchmarks as well. Because if you're comparing against an implementation that's really got a lot of fat in it, that's different significance than if you're comparing to something that's already very lean and optimized.
Yeah, I agree. That's my intention, is to always include a low level language implementation of the thing, so I can so I have at least some idea of where the space is between where I am and where I could be.
Exactly. Yeah. Thanks, Dave.
Thanks.
How far off prime time are you, Dave? Like, in terms of it being production ready?
I've done a lot of thinking to the point that I think it's, apart from debugging, a matter of just sitting down and writing the garbage collectors. I know garbage collectors are not trivial, but I have done this before, and I understand the parameters of what I'm trying to do well enough, I think, that I actually have a journal paper on garbage collectors, so it's not novel to me. And the garbage collectors are not rocket science that I'm proposing to do. There's some tricky aspects of can I get away without using a spin lock on this, or do I have to use a spin lock on it? But I think all the locks that I will need, spin locks are the right level, because they should be relatively low contention and very short interval with, you know, a couple instructions that have to be done in the locks. So that is my biggest concern, is that, you know, I'll run into a bug on one of those things. But and the method dispatch, I wrote an early version of that code, and I have all the hashing and so on stuff done. But that's the other piece that stands between me and being able to run hand compiled real code. And the code generator, I also have starts on to turn Smalltalk into threaded code. But that's probably the biggest piece that I have right now. But it doesn't, like, that will be a work in progress. I'll get it to generate working code, and then I'll start working on optimization and more inlining and so on. So, but my hope is sometime in the next 6 months, I should be able to run moderately real programs.
That's exciting.
Will I be able to run all of Pharo GUI? No, probably not. But and I have a grad student who's working on writing primitives. So I mean, as you saw, the primitives mostly are pretty straightforward to write. You just have to open the blue book, figure out exactly what they're supposed to do, and then just follow the pattern. So I expect to get most of the standard primitives at least done relatively soon. So, and that's kind of busy work that people could help with if they wanted to.
Interesting. Yeah, no, good. Exciting.
Yeah, I was the threaded thing. It was initially just for the same reason that the deck people did it back in the 70s. Initially it was just this is a fast way to generate code, and then as I explored it more and I realized that I could get this almost seamless transition between a debuggable threaded mode and a high-speed JIT'ed mode. It was a really revelation, I guess, in a way for me to realize how well that was going to work out.
Yeah, it's nice to get that. Yeah.
Yeah. So unexpected. So that was really rewarding, and the initial calculations on not real code, but on sort of standalone stuff for the dispatch also are encouraging. So we'll see.
Very nice. Very nice.
Yeah.
Hi,
Thank
David.
you all for your attendance. Yeah.
Hi, David. Peter Lound from Vancouver.
Hi.
Hi. Interesting talk. I find a lot of amazing things in your PDF of your presentation. I have a question about the parallel processing. How do you see that happening with, for example, with block forking? So how does someone do that and make sure their environment of objects are safe from multi-threaded conflicts? I'm sorry, I have a speech impediment from COVID stroke. So
sorry to hear that. Yeah, I mean, what you need to do is you need to use monitors or semaphores or similar things to manage the multi-processing, because if you don't, you'll get burnt sooner or later. And the problem is that because Smalltalk has run on a single processor for so long, there is code in the sort of common code base that assumes that that's the situation. And as I said, there is code. I haven't looked recently, but it certainly was at one point. The code for semaphore was basically just written as one piece of code that didn't send any messages and therefore was guaranteed to never be interrupted. And that's cool, but that's not realistic in a multi-threaded world. So, I mean, obviously things like that would have to be rewritten, and that's part of what I would do, obviously. But the challenge is if there are other places where people made assumptions about I can do this, I can do this, I can do this, and not worry about it, you know, fork something and then. But I mean, if you're writing forks already, then you should be using semaphores or monitors or something to control that concurrency. And if you've done that, you should be golden. There should be no hold up there. If you haven't, yeah, you're going to get bitten.
Thank you.
You're welcome.
Just one observation. In the self papers, the term that's used for taking a single inherited source method and compiling it into a bunch of native methods for each specific class, that's called customization. David Unger probably can tell you who came up with that term. I don't know who.
Thanks, Giselle. Yes, it was I who came up with customization. Sure. So I'm glad to see the techniques are still useful and good luck with them. I do think the inlining story will be refined as you learn more, Dave.
Yeah, I believe that.
The first paper that I ever wrote in English from 1994 was trying to evaluate how you decide to inline when you have multiple processors. Because if you have one processor, it's just a memory speed trade-off. The more you inline, the more memory you take up, but the faster it becomes. But if you inline and you have multiple processors, you lose the opportunity to run in parallel. Because the more you inline, the more sequential your code becomes, the less parallel it becomes. So that's a different space, a different trade-off that you have. I can put the link here. It's so old that it's compressed PostScript format, but basically I was trying to use adaptive compilation to explore that trade-off. And I was using a model where if you send a message to another object, you get immediately a future object as a reply.
Okay, yeah.
Eventually that object gives a proper reply that replaces the future. So there are two situations. You can try to use the future before it gets the reply, and then you block. Right. Or you can execute a lot and then either you never look at the future or you look at it after it's already been replied. By counting how many times you blocked and how many times you didn't block, that tells you if that particular message is good for inlining or not in terms of parallelism. So that's
great. Okay. Yeah, I've thought of. I mean, I'm very interested in the Beam VM and Elixir and Erlang, and I like programming in that model where everything is it runs in separate processes. And I've thought a fair bit, but not as much as you, obviously, about how to adapt that to a Smalltalk model of basically making. I mean, I'm not the only other person to have thought of this, obviously, but to make objects be real independent objects and just have everything be message sends and how, I mean, the cycles are where it gets really challenging, or at least in my thinking about it, that's where Okay, I got your link. Thank you.
Okay.
Yeah, so it's just a matter of if I could clone myself, we'd have this a lot earlier. Unfortunately, there's enough moving parts that it's hard to for someone else probably to even help with the project at this point. And that's a challenge for sure. But if anybody's interested, you know, let me know, and I'd be happy, you know, or clone the repo and you know, submit pull requests. But I would probably restrict myself to the primitives if that's something you wanted to do. But it would be a good way to get an understanding of how that stuff works. So if I piqued anybody's interest, that would certainly be something that where you'd have to understand kind of what's going on, and could be valuable. So. Any other questions?
I have a question about the first, one of the first slides you have. It says 64-bit and IEEE 768 standard. I searched for the IEEE 768 standard and I couldn't find anything, even on the IEEE website. What is that? Is it a floating point standard?
Yes, that's the floating point standard.
Is that where you're using to implement the 64-bit variability?
Maybe I got the wrong number.
Oh, in the slide?
I think it
Yeah,
might be
maybe it's
IEEE.
754. 754.
Oh, okay, that came out all the time.
Yeah, sorry.
Okay, I'm glad other people are doing typos.
Yeah. Sorry. Yeah, Wikipedia has a good article on it. Sorry. I'll fix that in my slide. Thank you.
Okay, thank you.
Sorry about that.
It bothered me.
I wonder if there exists the IEEE not a number standard.
Yes, well,
Yeah,
not numbers are tricky.
Yep.
Okay, sorry. It's updated in the slides now.
So you think?
Yeah, I'm
I
not the
know
first person to do this. So Spider Monkey, the Firefox VM uses NaN encoding. Although, so there are several different choices on how you do NaN encoding, but for me, having the floating point works best, because the reason is you can allocate an array of floating point values and then you can feed it to a GPU or something. Whereas if you use one of the other encodings, like the one that SpiderMonkey uses, doubles aren't doubles. So I chose this specifically because I wanted doubles to be doubles and then to encode everything else in the NaN space. So there are choices, and I think the Wikipedia page may talk about this a little bit, but certainly if you go and look at SpiderMonkey, you'll see their comments about the choices that they made.
On your slide, immediate values, you have a phrase NaN boxing. Could you explain that?
Well, the idea is that, so boxing normally means that you have that you put something in memory and you have a reference to it. And so NaN boxing is, rather than doing that, can we store the information in the object itself? So typical if you go back, I don't know how far you have to go, but if you go back fairly far, you'll find Smalltalks that used a single bit. And so if that bit was 1, let's say, then it was an integer, and if it was a 0, it was a pointer. And then more modern ones will use a couple of bits because they'll probably want to code characters as well. When there were only 256 characters, nobody cared. But with Unicode, you don't want to allocate, you know, a megabyte of space for character encodings, right? So so they got extended to include boxing characters as well as integers. And it's arguable whether there's any value in boxing. So I claim there is a value of boxing symbols, but it's arguable whether there's any value in boxing nil and true and false, because whether they're boxed or whether they're in memory isn't going to change very much. You're still going to, however, with them being boxed, it means that I have a constant value that I can compile to, that that I can, in what I'm inlining and comparing against it being this class or that class, I have it right there in the register. I don't have to go to memory, or I'm not comparing memory addresses. But if they were allocated in the global heap, which doesn't move anyway, it wouldn't be that different. So I don't know, but I think that it will be faster, particularly, well, I don't know. I go back and forth a little bit on this, but for now, it's not, I don't think there's any cost in doing this, in boxing them. And I'm not sure whether there's an advantage or not. But.
And
So,
large.
go ahead.
Sorry. Can I noticed you putting Unicode characters inside the boxed floating point format, or NAND format, but they don't seem to have the 24-bit. Are they the UTF-8 format for Unicode?
No, these are full Unicode values. So there's a little over 1 million possible Unicode values, and so that only uses 21 bits. So I have 24 bits available. So, or actually, I have 32 bits available. But so that certainly all the possible Unicode values fit in there. Until we meet aliens that have, you know, other languages and other alphabets, then we're good.
I noticed I didn't understand the page that details the formats of the boxed formats. I didn't understand the character format that starts with FF7 and 8.
Sorry, I'm going there. I have too many slides. There we go. This page.
The next page. Yes, yes. So character is F6008 and then 00, and then there's 6 hex digits for the character. That
right, which is 24 bits.
Oh, 6 or 24. Okay. I would put that as a Unicode character in the description type.
Sure.
I would just say Unicode. Yeah, that helps. And 24 bits. Okay, I get it. I am happy you're adopting Unicode. I think it's every Smalltalk has to do it, and not just as a side thing, as side Unicode string, but you know, this year they added 5,000 Unicode characters.
Right.
It's also almost 150,000 characters now.
Yeah, VA Smalltalk has an alternate version of string. So they have a Unicode string basically, and they're like my strings, as in they're not mutable, but they're beside regular strings. So they have regular 8-bit strings, and they have these Unicode strings, and they're not interchangeable, unfortunately. And I just, because I'm doing this from a clean sheet of paper, I just said, screw that, let's do it right. So
yeah, and it's nice that's boxing that you're doing, So 64-bit and can represent all of these different values and types in a register or a pointer field. And you don't have to have an object. I like that about from reading your paper or PDF yesterday. It seems there's a lot of optimizations that come out of the way you are choosing to do things.
That's the
By
hope.
reducing blocks and massive inlining of things. Now, I didn't understand what is this Giselle was saying about parallelism. Now, why it affected the different cores. Are you talking about the
Yeah, no, Giselle was talking about something a bit differently. It was talking about something using multi-cores in a different way. So he was talking about changing the way send worked so that you didn't get back a value, you got back a future. And this would be easier, like you could use
that's
F5
fine.
as a future, for example, if you wanted to. That would be very easy to do with this model. Yeah, I didn't mention it, but having the small integers at the end of the address space is actually quite nice, because you can add an untagged integer like 1 or 2 or whatever to a tagged one, and it's still a valid tagged value. You can compare them. If you do an unsigned comparison, you can compare 2 tagged values and get ordering right. So there's lots of things, and even if you're not sure they're both integers, you only have to check one of them. So there's lots of nice things about having the small integers be the end of that address space.
Yeah.
Dave, did you have a question or comment? Dave Unger?
Yeah, thanks, Dave. A couple of minutes ago, as you were answering one of Peter's questions, you described a decision. Oh, the batteries are dying. I'm going to have to switch to speaker. What bad timing. Well, I'll try this as long as possible. You mentioned some decision you made and then the rationale for your decision. And I just wanted to suggest that in a future talk about this, you tilt it differently. Instead of explaining how everything works, go through the decisions you made and the significance of each decision and why you made it and how it paid off or didn't. And that's a kind of talk I'd really wake up for. So just wanted to mention that, Dave.
Okay, thanks. Yeah, I like those kinds of talks too, because it's, nobody's going to probably Zag Smalltalk is not going to take the world by storm and is not going to become adopted by anybody, but hopefully there are lessons and perspectives that come out of it that will. So,
well, I mean, it's such a large undertaking what you're doing. The fascinating part for me is exactly that. What was your thinking? What did you decide, et cetera, and the details are, at this stage in my life, less critical to me, honestly.
I know the feeling.
Thanks, Dave.
Thanks. Anybody else?
I have to apologize for coming in late. My browser showed the time as being 1 p.m. PST, which is my time, and that was the end of your talk rather than the beginning. Okay. So afraid I messed up, but and I was able to, I took a quick peruse of the code base and took a look at the MD files in AST Smalltalk, the GitHub. And one thing I wasn't clear about looking at that was the environment structure for captured block closures. usually there's like in Scheme, you do escape analysis and you only create, you know, environments for sharing on something that escapes. You're familiar with all of that.
Yeah.
So I just, it wasn't clear to me. I really didn't see a description there of the block closure implementation. If you wouldn't mind going back through that just briefly.
I didn't really talk about block closure implementation. I've thought a lot about it, but I don't actually have them coded yet. But the basic hope is that the kind of inlining that I'm going to do is going to make most blocks go away. But blocks that don't will be allocated on the heap, on the nursery heap, and they will reference the context in the nursery stack of the object. One thing I didn't mention is that at some point in time you may need you may run out of stack space for context, at which point essentially all of the contexts get migrated to the stack and all of their pointers and so on all get set up properly so that happens. But the hope is, as everybody hopes, is that by allocating the block closure on the heap, on the nursery heap, and it will have a reference to the context, and then the returns, because so one of the challenges that people often have with JIT'ed code is that if they're using the native stack, then when they want to do a long jump, they have to unwind the stack. And what I have instead is that is really kind of classic Smalltalk before things got moved to the stack, in that the closure will point to a context. And so return basically says, return to that context. And it will be, you know, a dozen instructions kind of thing. So long or non-local returns are going to be essentially free. And hopefully most of the blocks will actually have been inlined as I inline the code that got past the methods that got past the blocks in the first place. Does that answer your question, or would you like more?
I guess the first approximation, again, it all has to do with capturing environments and sharing and closures that get invoked multiple times and those sorts of things.
Yeah.
Which if you're an old Scheme hacker, then that's become a big thing. Anyway.
Yeah. So
great, thank you.
The Pharaoh people, or I mean, I'll say the Pharaoh people, it includes Squeak people to a large degree too, but have done a reasonable job of, so basically if a field is, if a local variable is referenced in both a possibly escaping block and in the method, then they put those into they allocated an array, which would be allocated in the nursery, and that array is accessed indirectly from the context and also from the closures. And so all updates to those shared variables go through that. And that's exactly how I would be doing it, or how I will be.
Yeah, they used to call that a display in my day, but yeah, back when. Yeah. Okay, great. And FYI, the updated Fibonacci runs now on RISC-V. I sent you some email about that, but anyway, It's working now. Which says good things for portability. It does.
Good. Okay, thank you.
Great, thank you.
Anybody else?
Well, this is a very nice, it's very nice to see implementations with different design decisions and rethinking things and poking around, and then having the ability to measure. We all tend to get into sort of, stereotyped into common channels because of accepted wisdom. And it's when you make a variety of design decisions differently, then it really opens the space of your creative space up, which is a lot of fun. So great. Thank you.
Thank you. Yeah, I'm giving a version of this talk at virtually at a workshop in New Zealand on Sunday. It's virtual machines and implementation languages. I think it's called VMIL. If anybody's interested, I don't think you have to. Well, I haven't paid anything to join. So, but anyway, so if anybody's interested, and that talk is going to be about this as a multi-language VM. So I haven't started to write slides for it yet, but it's going to be a lot like this talk, except I'm also going to, it has to be shorter, but I'm also going to talk a little bit about how to support call with current continuation and a few other interesting challenges. So, which reminds me, I need to solidify those things, those thoughts in my head before Sunday. But
David, how would I find some ability to join that talk or listen to you on that presentation?
I just hang on a second. I'll put up a link to the conference. I don't know. Oops. So I have no idea what you need to do, but I will put a link to the talk, and if that helps you get to it, that would be great.
Appreciate that.
Yeah, so it's a workshop, so I'm hoping that some of the other people there will have some comments. I mean, I've really appreciated the comments I've gotten here, and hoping that we get some interesting challenges on, well, how would you handle this in this other language? But we'll see. So I think Tim and Giovanni have both disappeared. So I don't know when we should formally close this, but we're technically over time, but I'm fine if anybody has any more questions or comments, I'd be happy to answer or hear them.
To quote one old professor, I would say, depart in radiant contentment.
Yeah, that's good. So I will kind of call this in a couple of minutes. Does anybody have any? Oh, Craig has become co-host. Okay.
Somehow from
that was news to me. Sorry, Dave.
I was just going to say, somehow from the website, I haven't been able to figure out if one can attend virtually or they just want in-person people at Splash and Oopsla and everything.
I don't know. I'm giving my talk virtually because I was really excited with a conference in New Zealand. I thought I could take my family, but my family hasn't all been vaccinated. And so it was, nope, we're not going to New Zealand. Oh, Giovanni's back.
Yeah, sorry. It's a long process to put the baby to sleep.
Yes, I know the feeling.
It doesn't even work, right?
How old is your baby?
It's gonna be 5 months next week, so you know.
Oh wow!
They needs to learn how to sleep, basically.
That was fun times.
Indeed. Indeed. And Teams is
my youngest is 15 now, so it's a while ago that.
Yeah. Fair enough. Yeah, so it looks like I missed most of the second half, but what I saw was quite interesting.
Yeah, there seemed to be quite a lot of interest.
Yeah.
I appreciate all the comments.
Okay. So I just came back. I think.
Oh, go ahead. Go ahead,
Got any
Giovanni.
more questions? Sorry. I'll go again. Has everyone got any more questions for Dave? Or I think Peter, you were about to ask something. Oh, once you go off mute.
Yeah. On your memory management slide,
Yeah.
you talk about Fibonacci heap. I don't know that reference.
Yeah.
And similar to Mist. Now I've met the Mist guy, and he has a nice garbage collector idea. But could you give an overview of the way you're doing objects?
Objects are the heap. So must be here somewhere.
Memory management.
Yeah. So the idea is that you have a free list from the minimum size object you might allocate to the largest that will fit in these allocation units. So that means you'd have a free list for 2-word long elements, 4-word long elements, 8-word, and so on. And I thought I could replace the Fibonacci with binary, but maybe I missed one. But so when you want to allocate, say, an 8-byte, something that will fit in 8 bytes, you go to the 8-byte list and you see if there's anything there. If there is, then you lock it, verify it's still there, take it off the list, update the list pointer to the next thing, and then go off and use that 8-byte object space that you allocated. If there isn't any there, so you check and there's nothing there, then you look at the next larger size. You'd go to 16 and you'd see if there's any on that list. And you keep going up until you find a list that has something on it. And if you get to the last one, then you allocate a new one of these big spaces and fill it with objects and put them in the linked list and so on and so forth. But assuming you don't fall off the end, at some point you find a list that has an element in it. Say it's the 32 word list. So you take an element off the 32 word list, you split it into 2 16s, you put one of them on the 16 list, and then the other one you split into 2 8s, and you put it on the 8 list. And I don't remember what size I was looking for, 8, I think. So now you have an element that's 8, that's big enough for 8 words. Plus you've put a new one on the 8 list and a new one on the 16 list because you took one off the 32 list. Then you use your 8-word object and everything's fine. So, and then when the garbage collection comes along and it marks all of these, it takes blocks of, okay, I've got a block of this many words. What can I split this into? Well, it's, say there's 150 words free. Then it would take a 128 word chunk and it would put that in the 128 list. And then we have 32 left, so it would put the remaining 32 in the 32 list. And that's basically the whole story on the garbage collection. So you have all these free lists, which means that you can allocate very quickly. It's not quite as quick as on a copying collector, but it's pretty quick because you have these free lists of the appropriate size. So you never have to search very far for the right size because you know how much space you need and you can just go directly to that list. And if there's space, you're good. If there's not, you may have to go 1 or 2 up and possibly split some other ones up, but you'll get it pretty quickly. So the idea is that within 2 or 3 tests, you've found a block big enough for the allocation you need to make, which is almost as good as a copying collector. And then freeing them up is pretty straightforward because you just have chunks of available memory and you just split it up into power of 2 sizes and put them back in the appropriate list. I was originally going to use Fibonacci heap instead of a binary heap. And a Fibonacci heap's the same deal, except that instead of it being powers of 2, it's Fibonacci sizes. So you'd have a size 8, and then you'd have a size 13 and a size 21 and so on. So you do the same thing, except you have different, and it has a little bit less wasted space. But one of the experiments that I need to have this in fairly robust state before I can run is when I split something up, if I only needed 5 words, for example, and I got 8, should I take the 3 and put it on the to list? Or should I just consider it wasted space? So it's called internal fragmentation. So if you have internal fragmentation, is it worth, and maybe if it's above a certain size, it's worth it, and maybe not. I don't know. Anyway, those are the open questions around that. Does that answer your question?
Yes, and I have a earlier version of your paper.
Right.
So
Okay.
it's Fibonacci, not linked free list as your page here does.
Well, it's a linked free list in any case, but it's a question of whether it's Fibonacci sized units or power of 2 size units.
Yeah,
And misuse power of 2 size.
Yes, and you added an interesting aspect of recovering any lost space, like the 3 bytes, adding 2 of them to 2 bytes to the to list.
Right.
But how would you indicate that on the 8 list to free up?
So if I had 8, I got an 8 size piece, and I needed 5, then I would take the 5 and allocate it as my object. Then I have 3 left. So I don't support 1 word long things because I need a header and I need a linked list through them. So I need at least 2. So I basically would allocate the 2 onto the to list and mark the 1 as unused, so that when I collected it, it would be free space and collected.
So you have to collect with the, if you freeing an object on the 8 list, you have to check the 2 list and the 4 list to see if
not when you're freeing it, when you're allocating it. When you free it, basically you go through the whole page, and all of memory all of the page,
okay,
all the pages,
so
all the page every byte in the page has to be in some object, and so you just scan through them in order.
Yes. So you allocate 8, and you only are using 5, so you take 2 bytes and put it on the to list, and now you free up the object on the 8 list. But now you still have an object on the to list that is in 2 lists. How do you deal with that?
No. So when you took it off the 8 list, it's no longer on the 8 list. There is no. It's just a standalone object now.
What happens
to the 5? It happens to be 8 words long. There is no 5 list either. So it's not about lists anymore. We found the object, and now we have 8 words. And we can do whatever we want with them. But what we do is we allocate a header for the 5 that says it's 5 long. And then we allocate a header for the 2 that says it's 2 long, but it's free. So we put it on the free list. And we have 1 left over. So we mark it as 1 long, but we don't put it on any list because we don't have a free list for 1s. And then when we come to collect it, we scan through the whole page. We hit the 5 and we see it's still in use, it got marked. Then we skip over that to the 2 and we see that it's free. So we start we say, okay, this is free from here down, and then we continue scanning down until we hit something else that's in use. And then that block will be free and we'll allocate it onto the various lists. So
the 8 with the 5 bytes used would still be on the 8 list.
No.
Or it's in the.
So once you allocate it, it comes off the list.
Okay.
The list is just free things that we haven't allocated.
So you have to free up the space by freeing the two objects.
Yes.
Okay, this not on the freezes. You're correct. Yes.
Yeah.
It's very nice way of doing it for
Yeah, it is.
non-moving objects, because the generational garbage collection hits the caching in like they trigger the caching to bring back the memory twice. You have to do twice as much work, it seems, to do the mark sweep. Sorry, the generational collection, and mark sweep has less work to do in facting the inline caches. The translation look-aside buffers are not refreshed as much to load up the caching system. Do you know what I mean?
Yes, that is an issue, but it's beyond what I'm worrying about, at least now. Once I have a working system, so this is one of the questions of, for example, is when I allocate 8 words, should I just ignore the other 3, mark them as unused, but not put them in a free list, or should I put them in a free list?
It's not clear to me at this point which is the better solution, but
yeah, I don't know either. That would take some experiments, and it depends if an application needs a constrained memory usage. So it might be good in Peter Oldenau's case of having many threads on the web servers, having compact spaces. But if one, it might be a choice of mechanism. You have the mechanism to do both approaches, and then you set a policy. I want to constrain memory, or I don't want that memory. I might get some more performance by keeping a bit of wasted space.
Yeah, exactly. Yeah, and there's other questions like when I allocate them. So just as you're talking, I'm realizing that possibly I don't want to save any space. Like I don't want to reallocate anything that's smaller than a cache line, for example. That might be a so that I know that headers are always going to be, or objects are always going to start on a cache line, or at least above a certain size. Maybe, I don't know. Interesting question.
I'm working on a Smalltalk, and that is a decision I made. It's cache line is so important to not mix the threading of one core with the cache line of another core. So if an object is just on a single cache line of 64 bytes on an x64 processor, for example, 32 bytes on the 32-bit, but 64 bytes, that's 8 pointers. And in a way, you want that to be the minimum size, so that if an object is on a separate thread from another object, and they don't,
they're not gonna be threshing back and forth.
Yes, that's a big win on performance. It's huge. I talked with a professor in Australia whose team, I forget his name, I'm sorry. His team in the 80s and 90s unified the language for caching architectures, and Intel and AMD and ARM, etc. all have different caching architectures. So they were using weird language, and so this team unified all the language. And I had to talk with him a couple of years ago, and he pointed out that minimizing really you have three options. One is, what is a minimum size of an object? If it's the cache line, that's one policy. If it's splitting up the 8 into 5 and 3 and 2, that's another policy for memory, minimizing memory. But if you want to maximize machine performance, then you want to have minimum size of 8 on the cache line size. They want to be together to avoid multi-core thrashing of the cache lines, which slows down the processor by hundreds of cycles potentially.
Wow. Okay. Yeah. Thank you for pointing that out. I've just opened up about half a dozen pages talking about that. So I'll definitely read up about that. Thank you very much. I really appreciate it.
Yeah, you're welcome. I've thought about a lot about this, and I'm working on my Smalltalk for high performance parallelism. So.
Okay, cool. Yeah, that's a really good point. Okay, thank you.
But there's easy policies to pick, right?
Yeah, you just say what the minimum allocation size is and test it. Yeah,
you could run once you get the ability to compile all the Pharo code and run Pharo applications like a web server in Pharo with Seaside or something else, and you could have the policies go through pick each one, and then run the performance tests on them, and then let people choose. So that's one decision that I made a long time ago, is to provide the mechanisms and to let people choose their own policy for that set of mechanisms. So yeah, so it's a good decision, and I like that you're doing a compiled only version of your project, as well as the interactive. I think both are needed, and in my commercial uses, I am funded by projects that pay me. So I want to use Smalltalk, but I have code in Smalltalk, but I'm working in C++ and C. How do I get my code that's working without spending weeks rewriting it to C++? And I need a translator. So even if it's the Zig, that's compatible with C. So it would be good to have, even if you use Zig as the code base, have, I don't know how that's easily called from C or C++.
That's trivial.
I only learned about Zig yesterday. About
Zig, in fact, Zig has, some people claim that Zig is a better C compiler, so you can actually compile C code in Zig. And C++ is perhaps slightly more complicated, but C code, no problem. You can actually compile a .c file with the Zig compiler, and it understands it too.
You're making me happy.
Good. Now, if I can just get this to a point where you can use it, that would be even better, right?
Well, we can talk about that.
Okay.
Thank you very, very much for your presentation.
And thank you for your thoughts. I appreciate it.